Thank you, Jan, for the introduction. So as said, my name is Dominic Kempf. I'm a research software engineer at the Scientific Software Center, which is we were founded 1.5 years ago, and we are a research software engineering department that kind of works with scientists from all Heidelberg University on research software problems. The talk that I'm giving today is about binary distribution of Python packages. This is a very technical topic in itself, but I'm trying to keep a broader perspective on it and also try to motivate it why I think this is a very relevant topic for the research software engineering community. So let's start with stating that the Python language itself is a huge success story. So this is also evidenced by this TIOBE index for the popularity of programming languages that we can see here. And actually, in the last year, Python has risen to the top of that ranking and is now, officially by this index, the most popular programming language across all use cases, not only across scientific use cases. If we have a look at what exactly are the reasons for this success story and also restrict ourselves to research software, we can see a lot of features in Python that make it a very good fit for scientific purposes. And I mean, you might know a lot of these, but let's reiterate them. I mean, of course, Python's syntax is considered to be very intuitive and beginner friendly and a very good entry point for people learning their first programming language. And many researchers are starting with their research in the situation of learning their first programming language because their bachelor and master studies haven't qualified them in this area. I mean, this is a different area to talk about and we need to change this, but as is, I think Python is a very good fit to train these people a programming language in a short amount of time. Then it's a multi-paradigmatic programming language, so it's not restricted to one programming paradigm. You can do procedural scripting style programming as well as object-oriented programming, and it all fits well into one language. Then we have a very rich standard library that allows us to use higher level building blocks for a lot of common tasks, which is very important, I think, when teaching beginners to not have them spend their time with very low level activities. And then, of course, we have the availability of high quality, high performance scientific libraries, starting from the foundation work that NumPy provides to more specialized ones into very, very niche domain specific topics where there's a large ecosystem of very good scientific libraries available that allow us to prevent the reinventing of the wheel in the Python community quite a bit. Then, related to the high performance aspect of those scientific libraries, Python has a very good integration with compiled modules from other programming languages. So we can extend Python by writing C, C++, Fortran, Rust, whatever compiled language extensions. And this is the area that we're going to focus on today. And also for today, we have a standardized packaging and installation procedure. This hasn't been very good in the past because there was competing mechanisms, but I think right now we have converged to pip as the tool to install Python packages, and with PyPy, the Python packaging index, we also have a repository to store packages in. So we kind of have a very stable and well-established ecosystem to do that. Another success story is the Jupyter ecosystem that I'm pretty sure has contributed to the popularity of the Python programming language in science. And now let's focus on the aspect here, the availability of high-performance scientific libraries and compiled modules. So what we have here, I think, is a task for research software engineers, because we have here scientific users who have their programming knowledge is mostly limited to Python, and their toolchain knowledge is also limited to Python. They can do a pip install, but they cannot handle complex toolchains. But on the other hand, we have research software engineers who have a profound knowledge in more than Python, maybe C, C++, HPC topics, etc. And we'll also have a more complete toolchain knowledge, like including compilers, build systems, CI, CD, and so on. And I think the goal that we're pursuing is to create a separation of concern between these two user groups, so that within the limited like programming language and toolchain knowledge of the scientific user, they get access to performance-oriented codes that they would otherwise like not get access to. And now here's a gap of experience between the scientific user and the research software engineer. And I think, so what I'm going to talk about today is one aspect of building a bridge over that gap. And that is the installation procedure itself. Now, a few remarks about installation procedures. No matter how good your software, if it's not easy to install, it will not be successful. Then easy to install, to me, always means it's a standardized installation procedure. No matter how easy you consider something you came up with yourself, it will not be considered easy by other people, so it's not a good installation procedure. And the smaller the toolchain knowledge, or like the general like operating system, say for example Linux knowledge of your users is, the more important this aspect becomes. And I think it's often overlooked because you're sitting in your developer bubble, considering things easy that your users don't consider easy at all. And for like the specific case of Python with compiled extensions, I think the translation of the above would be only a pip install package name is an acceptable workflow. This needs to work. Maybe depending on what exactly your dependencies are, a conda install would be similarly okay, but I think conda install is just an extensive extension of pip install, so you should always be able to pip install your package. And due to the experience gap that we've seen before, I think no other requirements or dependencies on the end user side should be in an installation process. Okay, so let's have a look at what type of distributions for Python packages there are. In principle, there's source distributions and binary distributions. You can see that, for example, if you go to PyPy to any package and you go to the download files section, then you can see that there is source distribution, which is like an archive here, tar.gz. And then there's build distributions, which have like more complex names, which end on WHL, which is a wheel. Yeah, and we'll now have a look into what exactly are the differences and how we provide these in an automated way. So a source distribution, it's an archive. It contains all the sources of your project. They may be Python, C, C++, the build system, all of it. And a source distribution is absolutely necessary for your Python project, even if you want to provide binary distributions as well. This is for people to opt out of binary distribution, which I think is absolutely within their rights. I'm sorry about my camera, by the way. It's having this issue sometimes. Then it enables advanced use cases. For example, people that want to replace like the shared libraries of dependencies with other things. So it's kind of important to allow an installation from source. And then to comply with licensing restrictions, you might also be required to distribute the source. Then what happens during pip installation of a source distribution? The sources, the Python sources are copied into the installation tree, and the compiled modules are compiled on the user machine, which requires a compiler toolchain and requires dependencies of your, say, C++ code, which might be a huge thing and which might throw very unpredictable errors on the user side if he doesn't fulfill the necessary requirements. On the other hand, we have binary distribution as so-called wheels. So a wheel is a single archive file that contains Python sources, the package metadata, also compiled modules in the form of shared libraries. So a compiled extension is basically a shared library that's kind of built with according to like the certain standards. And then it might also contain additional shared libraries which are bundled because they are needed for the compiled modules to work. And then a wheel file has a very complicated name that has several tokens which are separated by dashes. And the first one is the package name, then there is the package version, then there is an acronym for the interpreter version. For example, CP39 means the CPython interpreter 3.9. Then there is an RB compatibility tag, and there is a platform tag, which may, for example, be WinAMD64 or many Linux 2014. There's a whole list of these that pip understands. Then at installation time, pip will query PyPy what wheels there are. If there is a suitable wheel for the given platform, it will download that wheel and it will copy the shared libraries into the installation tree. And if it doesn't find a compatible wheel for this platform, it will fall back to the source distribution. So let's talk about providing these wheels ourselves, because they give us a lot of advantages. They allow users to install our package without a compiler on their computer, and they drastically speed up the installation process because it's just downloading and copying a shared library instead of building it ourselves. So, but what are the pain points about it? So why doesn't not all the projects do it just like that? Okay, first question, if you haven't come across that question, is like, given you have already a C++ code base, how can you create maintainable Python extensions in compiled languages? This is maybe not really related, but I want to also target that for a moment. And then how do I define a build system that successfully and robustly compiles these Python extensions on a wide range of platforms? Because for source distributions, this will be on like your user's computer. So it's really absolutely necessary that you have a very standardized, robust build system for that. Then how do we manage the compilation of wheels for the combinatorics of Python versions, platforms, etc.? So it's potentially a very large number of wheels that need to be built, and you don't want to maintain that process manually. And then how can we automatically deploy that to PyPy using a continuous delivery process? And in the following, I present tools for each of these pain points, and hopefully I'll convince you that there is easy solutions to do all of that. So first of all, let me make a small pitch for PyBind 11, which is a C++ 11 library to generate Python bindings for C++ code. And I think it's really a very, very powerful tool. So it's header only. That's remarkable because other tools that generate Python bindings use additional tool chains like source code generators, etc. So now this is like you're writing one C++ source file using the header only C++ library PyBind 11. This compiles into a shared library, and this shared library can at runtime be loaded by the Python interpreter. PyBind 11 comes with CMake integration. So if you're already using CMake for your project, you have a very, very standard, straightforward integration into your project. And it's in general very well designed and very well documented. So this is actually one of the libraries that I enjoyed working with the most in my career as a developer. So you should really try it. One thing that comes in very valuable also from the scientific point of view is that it has optional opt-in type conversions, which allow you to automatically convert types on the C++ side into objects on the Python side. For example, you write a C++ API that takes a standard vector, and you generate a Python binding for that. It will automatically accept a Python list as an argument. And same for many other STL container types. Then it has an optional type conversion for NumPy arrays to eigen3 matrices. Eigen3 is, on the C++ side, one of the most popular linear algebra libraries. And NumPy arrays are the standard of array computing in Python. So you get interoperability between these two already implemented. And something also very nice, like you have Python callables like functions, and you can pass them to any C++ API that accepts std function as an argument, and so you can, for example, extend a C++ function with a Python callback, which is a very powerful mechanism in itself. And just to show you like a few lines of Python 11 code, so this instantiates a module which on the Python side would be called my module. On the C++ side, it's an object M. This is generated through a macro. And then here within this body, we can, for example, expose a function, my function from our C++ library, just by like passing the function pointer to that, and it will do introspection of the types and do the automatic type conversions needed to expose this as a Python function, my function. Same goes for classes. We can like define a class by putting the C++ class as a template parameter, and the name on the Python side as a parameter here, and then we can define properties of that class. In this case, we're just exposing like a property that can be read and written from the Python side. But there's a lot of more functionality. Just read through the documentation. So once we have that, we had a C++ library, we generated bindings for it with PyBind 11. How do we design the build system? So we have a CMake build system already that builds the C++ code and builds the shared library that is the Python extension. So how do we glue this together with the Python build system? Because the Python build system is defined by setup.py. And now you could do this manually, which would lead to like around 50 lines of code being added to your setup.py, explaining pip how exactly to invoke CMake and how to like build the project and then copy the build artifacts into the Python installation tree. Fortunately, because these 50 lines of code aren't super readable and super maintainable, there is a project that abstracts all of that, and it's called scikit build. So what scikit build does is it wraps around the setup tools setup call. So you don't do from setup tools import setup, you do from sk build import setup. Then, as denoted here by the dots, you get all of the arguments that setup tools takes, and you can pass additional CMake arguments. And so what it does during pip install, it runs the CMake lists file from your root directory and builds that into a temporary directory and automatically installs the artifacts into the Python installation tree. The dependency on scikit build itself and on CMake, actually, you can specify that in pyproject.toml, which is a new metadata file that allows you to specify requirements of the build process itself, which was not possible in Python before the introduction of that new file. So now, how do we manage the build process in continuous integration? And the answer to that is CI build wheel. So CI build wheel is a Python project which like recognizes which CI provider it is run in from the environment, and then sets up the environment for like building wheels for all the like recognized types of wheels for different Python versions, for different platforms, etc. So it manages all of that variability. It integrates with a lot of tools like GitHub Actions, Azure Pipelines, Travis CI, AppWare, Circuit CI, GitLab CI. And it allows us to customize this process. So the process is split down in four steps. First, it sets up the build environment. Then it compiles the wheel. Then it repairs the wheel. That's a curious process. I'll talk in a minute about it. And then it tests the wheel. So it also runs your unit tests on the binary distribution that you're about to ship out. And the configuration of all of that is also done through pyproject.toml. So here's what it looks like in your CI log, for example. It says like, okay, let's build this wheel for Python 3.6, Many Linux x86, and then it sets up the environment. You could, for example, in here, by configuration, install additional dependencies. Then building the wheel is actually a pip, the operation that runs setup.py to build a wheel. Repairing the wheel is like taking the the wheel and making it self-contained such that it can run on other systems. And this includes copying shared libraries into the wheel that are necessary for the shared libraries in the wheel to work. So the tools that do this are like different on each platform because the mechanism of shared linkage is different on each platform. For Python, it's called audit wheel. For macOS, it's called delocator, and for Windows, it's called delve wheel. But they all do the same thing. They kind of take shared libraries that you depend on, copy them into the wheel, and rename them to like make to avoid name clashes when multiple copies of a single library are present. But what you get is a self-contained wheel that contains like your compiled modules and all the dependencies into it. Of course, if you don't trust this process, you can always just try static linking instead. So you get bigger shared libraries that contain the symbols that you need. And now, how does the release process look like? I'm showing this for GitHub Actions, and there's good reason for that because there's good support by PyPA, the Python packaging authority for that. It provides two actions. First of all, a CI build wheel action that is that runs the wheel building jobs for you. And then there is a GitHub action PyPy publish action that actually deploys to PyPy directly if you have your API token in the repository's secret. And so a reason to use GitHub Actions here is also that GitHub provides us with runners for Linux, Windows, and macOS for free. And it's kind of the only of these large providers that do that currently. And we need all of these to like provide wheels for all the platforms. The entire release workflow is written in a GitHub Actions workflow file. I usually do this in a separate workflow, and this workflow triggers, so it's executed on like when you manually trigger it, or if you create a release on GitHub. And this is the dependency graph of the entire release process. Then we like build the source distribution. We test the source distribution by like building the package from the source distribution to ensure that it contains all the things that we wanted to. And then here's the build wheels job. So you see that there's a Linux, a Windows 32-bit, a Windows 64-bit, and a Mac OS-bit job, and they all build wheels. They upload their artifacts on GitHub Actions, and then there is an upload to test PyPy and an upload to PyPy job, which download these artifacts created in the earlier jobs and push them on test PyPy or PyPy. And this is a very simple process that you can manually trigger, and it does the entire thing across all platforms for you. So I'll now show you 3 examples from our work. So the first one's called Py4DG. It's an ongoing research project that the Scientific Software Center is involved with. It's about the spatiotemporal analysis of point cloud data acquired by airborne laser scanning. The group that we're working here is primarily interested in geomorphic changes, and this has certain high performance needs because it has very compute intense algorithms, and it's very well possible to exploit multi-core systems with that. On the other hand, the geoinformatics community is very Python oriented, and it's very interesting to integrate that into a larger Python ecosystem. And NumPy arrays already provide a great interface in terms of data structures. So we implemented all of this, all of what I've shown you here, and it actually works quite nicely for that. You can have a look at the project, but it is still work in progress if you're looking at it very closely.
Dominic, Marcel raised his hand. Maybe you allow a question in the meantime.
Yeah, I have 2 more examples. I go through that very quickly and then I'm finished, okay? So the next one is we packaged Clang format for this. So this is just to say that you can even package non-Python code using this toolchain just by having statically linked C++ executables that are wrapped by like a thin Python wrapper. And we did that to enable like pre-commit hooks that use claim format. And the third example is that if all of this was too theoretic for you, we have a cookie cutter, which is like a configurable template repository that implements all of what I just said. So you can just run these two commands here, and you'll get a no-op Python package that you see all of this set up and in action, and you can customize it for your own needs. So now I'm finished, and now I'll happily answer a few questions.